I've replaced all the fusible resistors in the power amplifier sections. It appears that 10 ohm and 100 ohm fusible resistors are easy to obtain. However, the other values called for seem not to be available or are very expensive in small quantities, so I've just used ordinary resistors for those. I noticed a couple of discrepancies with the service manual. They were that this resistor here, R735, in both channels is marked as being 270 ohms on the diagram, and that's what I found installed, but the parts list said 330 ohms, so that's what I've used for now. I'll have to wait and see whether or not that was a good choice. And also this resistor up here, R718, is marked as 82 ohms, and that's what the parts list says too. However, I found 68 ohm resistors installed there, but I've gone ahead and replaced those with 82 ohms as shown on the circuit diagram. I've already carried out a few tests, and the good news is that the large DC offset that was present at the output of the right hand channel has gone, but sadly all is not well. I connected my multimeter set to measure DC millivolts across this output emitter resistor. The service manual says that then these controls should be adjusted to give 7.7 millivolts across that resistor, which corresponds to a quiescent current of 35 milliamps through the output transistors. I was only able to adjust for about 20 millivolts across that resistor, and as time went on that value was slowly increasing. The left hand channel was a bit better. I could adjust for about 10 millivolts, but not any lower, so I think that's still not quite right. And after the amplifier had been on for a number of minutes, the right hand channel's heatsink was getting quite hot, whereas the one for the left hand channel was still at more or less room temperature. I've been investigating the situation with this oscilloscope, and now the probe is connected to the output of the right hand channel of the amplifier, and I will now switch it on. Just heard the output relay click. And then after a bit of a delay, this oscillation at around 10 to 11 megahertz that I saw before appears. I've connected the other oscilloscope channel to the output of the left-hand amplifier channel, and if I enable that, we can see that basically the same signal is present there, although at a lower amplitude. I think the two must have a common origin. I think the onset of the oscillation is somehow temperature related, because if I turn the amplifier off and then on again with only a short off time, then the oscillation appears straight away. If I turn it off for a number of minutes and then turn it on, there's a delay again before the oscillation starts. Also, I've tried gently heating various parts of the circuit board using a hairdryer, and that does change that changes the frequency of the oscillation, and the effect of that is most noticeable when I aim the hot air towards the right hand channel power amplifier section. To see what effect the oscillation has on my attempts to set the output transistor's quiescent current, I've connected the oscilloscope's inputs to either side of one of the output emitter resistors, and the red trace shows the voltage across the resistor. It is at or close to zero for most of the time, but there is a pulse of current passing through the output stage around the zero crossing point of each positive going part of the waveform. Clearly the reading from a DC voltmeter connected across this resistor will be nonsense. While it doesn't look like much, these pulses are causing excessive power dissipation in the output transistors. I fear this is going to be a difficult problem to resolve. I can find the unwanted oscillation at almost all points in the system, in both power amplifier channels and on the power supply rails, so it's difficult to pinpoint the origin. By the way, these connections here are simply to tie the heat sinks to the 0 volt power supply line, which is how they'd be when the amplifier is installed in its chassis. Sometimes this can have an effect on the stability of an amplifier, but it doesn't seem to have made any difference in this case. I've also been experimenting with adding additional capacitance between the base and collector of these two transistors. This adds additional local negative feedback at higher frequencies. When added between the base and collector of Q703 for either channel, it makes a significant difference to the amplitude of the unwanted oscillation at the output, but doesn't remove it. I also noted that if, for example, I add the capacitance only in the right-hand channel, that it doesn't have any effect on the output of the left-hand channel, and the same the other way around. I have removed both of these pairs of transistors from the right-hand power amplifier channel. I did that to disable it so I could determine whether or not it was the thing oscillating, and then I could work on the other channel without having to worry about any coupling of signals between the two. So in this state, there's no output at all from the right-hand channel. However, there's still a 10 to 11 MHz oscillation from the left-hand channel. I've removed those same transistors from the left-hand channel, and now I can find no trace of any high-frequency oscillation anywhere in this system. So I think I have to conclude that the source of the oscillation was the left-hand power amplifier channel, or it along with the right-hand channel. Quite a lot happened during that moment of blackness. First of all, I reinstalled the transistors that I'd removed from the right-hand channel, so that I could test the amplifier with only that channel present, and I wasn't too surprised to find that it oscillated just as before. Then, remembering that previously I'd experimented with adding some extra capacitance across these two capacitors here, I removed those capacitors. I tested them, they both measured about 22 picofarads as indicated and didn't have any measurable leakage, so I don't think they're faulty. However, I replaced them with a single 100 picofarad ceramic disc capacitor, switched the amplifier on again, left it running for about 10 minutes, and there was no sign whatsoever of any oscillation. I then reinstalled the transistors in the left-hand channel, switched on the amplifier, and after not long at all, oscillation was present at the output of that channel, and the same signal at the output of the right-hand channel, but at a lower amplitude, so obviously the signal must have coupled from one channel into the other. I then made the same capacitor swap in the left-hand channel, and had the amplifier on for about half an hour, and could find no sign of any oscillation whatsoever. I was able to set the output transistor bias point and DC offset as described in the service manual, and they remained relatively stable over that whole time. So it looks as if that may have cured the problem. I feel slightly unhappy because I've changed apparently non-faulty components for a replacement that's not the same value as the original. Of course, I haven't got an original working example of this amplifier to test, so it may be that this design always has been prone to high frequency oscillation, and that over time, as other component values have drifted just a little bit, it's pushed it over the edge. I've reinstalled all the parts in the chassis, following thoroughly cleaning everything. I've had the amplifier switched on for several hours. I've been listening to some music through it, and I've not noticed any problems. From time to time, I removed the input signal and checked the quiescent current through the output transistors. It varied quite widely from the value I'd initially set it to, but I didn't notice it become unreasonably high. I'm not too surprised about those large variations because, so far as I can tell, the only thermal compensation is due to the action of a pair of thermistors in each channel, and neither of these are connected to any of the power transistors or the heatsink, so they can only adjust for long-term average temperature changes. That led me to think again about these heat-resistant sleeves that were originally slid over some of the transistors, and I thought that perhaps they were there to reduce the effect of temperature changes on transistors that don't generate very much internal heat themselves, and that would allow the slow action of the thermistor-based temperature compensation to be more effective. So I referred to some photographs I took before I started work and worked out which transistors had those sleeves on. I found it to be these two driver transistors, well, pre-driver transistors, sorry, and that makes a lot of sense because changes in their temperature would certainly affect the output quiescent current. There was also one over this transistor here, and I'm less sure why that's important. I haven't mentioned this section of circuit before, but so far as I can tell, it's another protection mechanism. This transistor here monitors a portion of the voltage across this output emitter resistor. That portion is influenced by the temperature because of this thermistor, and if the current through this output resistor should exceed some threshold, then these transistors turn on and remove the drive from the base of this transistor here via this diode. So in normal operation, that diode should be reverse biased, which I have confirmed is the case by measuring the voltage across it. Also, this transistor here in the voltage regulator system had a sleeve slid over it, and I'm not too sure why that was necessary either. These two transistors work as fairly ordinary pass transistors in the voltage regulators, and these two and their associated components arrange for the regulators to shut down in certain conditions. This one up here monitors the output of the negative regulator, and if that goes away or becomes too high, then it shuts down the positive regulator. And this transistor here is set up so that if the AC voltage from the mains transformers goes away, then it shuts down the negative regulator. This system should mean that both regulators are shut down rapidly as soon as the mains is turned off and before the reservoir capacitors discharge. While the amplifier was running, I also noticed that those two pass transistors, these power packages down here, became extremely hot. I measured one of them at over 70 degrees centigrade, and that was on a fairly cool day. So I'm worried there could be problems there if I were to run this amplifier during warmer weather. So I'm going to have a look and see whether I can install a small heatsink there to improve that situation. I will also reinstall the thermal sleeves over the transistors in the power output stages. I've used a piece of thin sheet steel to fashion a simple heatsink for the voltage regulator transistors, and it's now installed down here. I used an insulating pad between the transistors and the heatsink because, as is common for power transistors, their collector is connected to the metal tab, and the collectors of these two transistors should not be connected together. This amplifier is switched on. It has been for a while now. A temperature probe held against the tab of the regulator transistors reads about 60 degrees centigrade, so that's a useful improvement over the 70 degrees or above that was the case before. They now operate at about the same temperature as these pairs of transistors down here, and they are this differential stage here in the output amplifiers. I'm a little bit surprised that they're operated with enough current through them to make them get that warm, but I don't think it's a problem. This amplifier certainly wasn't designed with energy efficiency in mind. Even worse, these two power resistors down here operate at about 80 degrees centigrade, and so far as I can tell from the circuit diagram, they are simple dropper resistors used to generate the power supply voltages needed for the front panel display lights. I'm now going to go through the setup procedure to set the output transistor's quiescent current and the output DC offset. This multimeter is set up to read DC millivolts, and I'm going to connect it across one of the output emitter resistors in the right hand power amplifier channel. The service manual says that then this control here should be adjusted to give 7.7 millivolts across that resistor, and that corresponds to a current through the output transistors of 35 milliamps, assuming the resistor is accurate at 0.22 ohms. Now I'm going to set it for slightly lower voltage than that, around about 7 millivolts, because I know from recent experience that when this amplifier has been operating for a while, actually with a signal running through it, then as the temperature increases, the quiescent current through the output stage increases by quite a bit, so I don't want that to get too high. So I will adjust this maybe for around 7 millivolts. And as is usual for these things, the adjustment is very sensitive and it's difficult to get to exactly the desired reading. That's probably close enough. The manual then says that this control here should be adjusted to give a minimum reading possible, but that minimum should still be within 2 millivolts of 7 millivolts. One should then return to this control and try to return it as near to the desired point as possible. So let's try adjusting this. Increases in that direction. This is a very sensitive control, and I'm hardly turning it at all. Now it started increasing again, so I'll go back a tiny little bit. It's so sensitive it's difficult to find the exact point, but it's clearly about where it is now, and I want the voltage across this resistor to be about 7 millivolts, so I think I'll leave it at that. Now I'll move the connection across to one of the emitter resistors in the other channel and do the same thing. I think this control was already set for the minimum point. Finally, it says that these controls here, one for each channel, should be adjusted to give the minimum possible DC offset at the output. So I will change these for more conventional multimeter probes and connect the probes to the speaker sockets at the rear. It's connected to the right hand channel, I believe, so I will now adjust the control to reduce this reading as close to 0 as possible. And this control is even worse than the others. The tiniest movement causes an enormous change in the reading. I have adjusted this before and found that once the amplifier has been operating for a while, the reading does normally settle down to around about within 20 millivolts of 0. However, when it's first switched on and before everything's warmed up, the reading can be over 100 millivolts, which is perhaps not ideal. I think that's about as close to 0 as I'm going to be able to get. So I'll leave it at that for now and move over to the other channel. Then the control suddenly jumps a little. I think that'll have to be close enough. I thought it'd be fun to return to the analog oscilloscope. I've now got a signal generator set up to inject a 1 kHz sine wave into both input channels of this amplifier, and the oscilloscope is connected to the speaker output of the right hand channel. If I adjust the volume control, we can see that the signal clips almost perfectly symmetrically and at about 100 volts peak to peak, as we've seen before. I'll move the probe over to the other channel. And the result appears to be identical. If I turn down the volume control and zoom in on this signal, it looks perfectly clean. There's absolutely no sign of high frequency oscillation, and I can assure you that exactly the same applies to the other channel. The oscilloscope is still connected to the loudspeaker output of the left hand channel, and I've also connected an 8 ohm power resistor to the output of that channel. There is no load on the right hand channel, and I will turn the volume control up to the signals at close to the output is at close to its clipping point. About there. And that's around about, well, almost exactly 75 volts peak to peak. So if I type some numbers into my calculator, that tells me that the amplifier is delivering about 86 watts RMS into the 8 ohm resistor. I've repeated that test on the other channel and the results were identical. Now I've got an 8 ohm power resistor connected to the output of each channel, so we can see how much power the amplifier can deliver when it has a load on both channels. The oscilloscope is still connected up to the output of the left hand channel, so I'll turn the volume control up until the signal is close to clipping. About there. I just move the probe over to the output of the other channel, check that's behaving similarly. And it is, although perhaps it's clipping slightly sooner. So adjust that to there, and we'll measure that peak to peak voltage. (65, 66 volts peak to peak). I'll turn the volume control down because I've only got small heat sinks on these power resistors. I don't want them to overheat. So 66 volts peak to peak, I'll type that into my calculator. And that tells me that's about 23 volts RMS, which across 8 ohms is 66, almost 67 watts RMS into both channels simultaneously. This amplifier's stated rating is 50 watts per channel, so it seems it can certainly manage that. When performing this sort of test, it's important to realize that this type of amplifier is normally not designed to be able to deliver its maximum rated power continuously, so it's best only to run this test for a short time. There are a few qualitative tests that it might be interesting to try. Still got an 8 ohm load connected to the output of both channels. If I adjust the time base to zoom in, there's certainly no visible sign of crossover distortion, so that's very good. How about trying a square wave instead? Now if I enable the front panel tone controls, we should see an effect on the square wave. So that's with the treble control, the bass control turned to maximum boost. Now to maximum cut, put it back to the center, and with the treble control turned to maximum boost, and now to maximum cut. So it certainly looks as if the tone controls are having the right sort of effect, and as I mentioned earlier, I have been listening to music through this thing and can confirm that they work as expected. I've switched back to a sine wave test signal, so let's try a different frequency, say right at the upper range of the frequencies this thing should be able to cope with, and let's go to 20 kHz. There's a 20 kHz sine wave, and it appears the amplifier can handle that perfectly well and produce the same level of output power. Could try going a bit higher. Here's 30 kHz, and it seems there's no problem with that either. I will consider this repaired. I might return to it at some point to make some more detailed measurements of its performance, and I'd like to investigate the superlinear circuit to see whether it gives the advantages that Hitachi claimed it did back in the 1980s. But for now, I'm just going to use it. Sadly, I can't let you hear that, otherwise small fluffy animals might be tortured, or perhaps the universe would implode.